Welcome. This presentation will be about modeling and simulation of the energy regenerative system for active horizontal seat suspension driven by an induction motor, prepared by Maciejewski, Peckold, Krzyzinski and Krolikowski, from Koszalin University of Technology in Poland. The presentation will proceed in the following order. At first, a brief introduction and purpose of the research will be presented. Then simulation model of the active horizontal seat suspension will be discussed together with its experimental verification. Then motoring braking principle of an induction motor will be presented and a concept of the energy regenerative system will be proposed. Finally, the brief conclusions will be announced. The energy recovery suspension system captures energy generated during vibrations, which can significantly mitigate vehicle oscillations and enhance power supply efficiency. The concept of an energy regenerative system for active horizontal seat suspension driven by an induction motor involves using the motion of the seat to generate electrical energy that can be stored and reused to power the seat suspension system. Energy harvesting from car seat suspensions is a relatively new area of research, but there has been a growing interest in this field in recent years. Several studies have demonstrated the feasibility of energy harvesting from car seat suspensions using piezoelectric, electromagnetic, and electrostatic harvesting techniques. The energy output from car seat suspensions is relatively low, typically in the range of a few watts to a few tens of watts. The energy regenerative system for active horizontal seat suspension driven by an induction motor is a concept that aims to enhance ride, comfort and energy efficiency in vehicles. By actively adjusting the seat position based on real-time vehicle motion data, this system can provide a smoother and more stable ride experience for passengers. The moving part of the mass load M is connected to the suspension frame by using two tension springs of the stiffness CSX and one shock absorber of the damping ratio DSX. There is friction of the suspension mechanism considered in this paper and the frictional losses are represented by the friction coefficients X. The mechanical system is put into motion through the kinematic excitation QSX that is caused by external disturbances coming from the road roughness. The active subsystem is employed to reduce harmful vibrations of the suspended body. For this reason the permanent magnet synchronous motor, PMSM, is used as a modern actuator that generates the active force FAX. Such an active force is produced by the electromagnetic torque of an induction motor that in turn is controlled by the programmable power supply. The equation of motion describing the active horizontal seat suspension driven by an induction motor consists of the following forces, where Qx is the displacement of suspended body, m is the mass load, dsx is the viscous damping coefficient of a shock absorber, csx is the stiffness of particular tension springs, sx is the kinetic friction coefficient, g is the gravity constant, qsx is the displacement of input vibration, T is the electromagnetic torque of a motor and Re is the length of a lever arm. The electrical system representing an induction motor assumes sinusoidal flux distribution that is established by permanent magnets, hence D-axis and Q-axis currents are given by the following relation, where R is the stator resistance, P is the number of pole pairs, LD and LQ are the D-axis and Q-axis inductances.
Μικρό λάμδα
is the amplitude of the flux induced by permanent magnets, U and are the D-axis and Q-axis voltages supplying an induction motor. The electromagnetic torque of a motor is produced, because of the calculated above currents ID and IC in the following way. The suspension system is mounted on the vibrating platform that generates random vibration by using a programmable electro-hydraulic shaker, Fig. C. The system under investigation is loaded by a rigid mass that is affixed to the upper part of a suspension mechanism. Its oscillatory motion is regulated by active force that is applied by the PMSM motor through a two-linked mechanism. Such a mechanism converts the rotational motion of a motor into the translational motion of a suspension system in the longitudinal direction. As follows from the presented figures, the simulation results match the measurements reasonably well. Minor discrepancies between computer simulations and laboratory measurements are caused by imperfect modeling of the force characteristics that strongly influence the vibro-isolation properties of a suspension system. However, in general, the proposed model is representative of most suspension systems and its parameters can be evaluated for a specific type of seat. As with most passive systems, Figure, the amplification of vibration amplitudes is occurred around the resonance frequency between 0.5 to 3 Hz, and the required damping of vibration is obtained in the over-resonant range above 3 Hz. The developed active system, Fig B, significantly reduces the resonant vibration of seat suspension by applying the electromagnetic torque of an induction motor. In this case, the vibration transmissibility is lower than 1 over the whole frequency range 0.5 to 12.5 Hz, therefore the desired effect of vibration isolation is achieved. When braking an induction motor, electric energy is returned to the servo drive system. Mostly the programmable servo drive is equipped with an integrated braking resistor which should convert the braking energy to heat. In Fig, a simplified model of the active horizontal seat suspension is presented and graphical illustration of the motoring braking principle of an induction motor is shown in Fig B. In accordance with the electromechanical analogy, the braking can be achieved if the desired force, Fax, des of an active actuator and the relative velocity qs of a suspension system have the opposite signs. Otherwise, an electric actuator operates in motoring mode and therefore it must consume energy from an external power supply as follows, where kBRK is the constant coefficient representing the braking force of an induction motor. In order to realize the control strategy, the following electrical circuit of the PMSM motor with braking resistor RBRK is proposed and defined in rotating reference frame, DQ frame. Such an electrical configuration allows for operating the PMSM in motoring mode, red circuit for the purpose of generating the desired active force, Fax, des if it has the same sign as the relative velocity of a suspension system. Then the PMSM motor is controlled by a programmable power supply that generates appropriate voltages. UT. In braking mode of an induction motor, an external source of supply is disconnected, and the kinetic energy of a rotating rotor produces a current flow in the electrical circuit blue color, with braking resistor. The regenerated currents, ID, Regen, I, Reg can be therefore used to charge the batteries, which is called as regenerative braking. Time history of the actual force generated by the PMSM motor is shown in Fig A as follows from this figure. The desired active force is well reproduced by the PMSM in motoring mode. However, the system in regenerative braking mode is not effective enough for following the desired force precisely. The transmissibility behavior of a regenerative suspension, Fig B, points out higher vibration magnitudes in the low frequency range, up to 4 Hz, but at higher vibration frequencies each suspension system, that is, passive, active and regenerative, works similarly. Due to low force of the PMSM motor induced during its braking, the regenerated power amounts only 3% of the overall power consumed by the full active system, Fig C. Such a small amount of the regenerated energy is caused by an insufficient angular velocity and induction motor, therefore an additional mechanical transmission system is required. In the subsequent project, a novel control design methodology will be devised with the aim of enhancing the suspension dynamics, thereby effectively mitigating vibrations transmitted to the human body. The unique system architecture is intended to facilitate the identification of a control algorithm that delivers the desired closed-loop responsive active vibration reduction systems within a specific frequency range while minimizing energy consumption during operation. An advanced programmable microcontroller algorithm determines the desired active force, Fax, des be generated in the vibration reduction system to counteract the kinematic excitation QSX. Subsequently, the author's proposed model for energy regenerative electromagnetic actuators should be established to facilitate advanced control synthesis in conjunction with vibration energy harvesting. The inverter switching scheme, managed by the programmable microcontroller unit, will be designed to optimize energy recuperation during the energy regenerative vibration reduction process. The central concept involves utilizing a three-phase synchronous motor in tandem with inverter switches, functioning as a boost converter and enabling the reversal of phase currents back to the DC bus capacitor. The energy regenerative vibration reduction system will be accomplished by controlling specific switches, power MOSFET transistors, via the PWM signal. Electricity recovery in the vibration reduction system will occur by controlling the inverter's lower transistors T2, T4, and T6 through the PWM signal and deactivating all upper transistors T1, T3, and T5. This procedure permits the reversal of phase current direction, allowing electricity to flow to the capacitor. The performance of both passive and active seat suspensions was analyzed, with the active system shown to significantly reduce resonant vibration by applying electromagnetic torque from an induction motor. The energy regenerative system makes use of a braking resistor to convert braking energy into heat and a three-phase synchronous motor to optimize energy recuperation during the vibration reduction process. Although the current regenerative braking system regenerates only 3% of power, the researchers plan to develop a novel control design methodology to enhance the suspension dynamics and minimize energy consumption during operation. The following references were used during preparation of the presented paper. Thank you for your attention.